Hey, super fast review for our test over law of conservation of matter. What we want to try to keep in mind with our law of conservation of matter is just remember we're surrounded by matter. Everything that exists is matter. It's made up of atoms. And while it may seem like there's changes constantly going on around us, in which they are, matter is constantly changing, but the atoms that make up that matter remain unchanged. So what we mean by that is, for example, carbon, which makes up so many of the things around us. It can be in sugar, it can be in carbon dioxide, it could be in gasoline, but the atom itself doesn't change. The carbon that's in this apple when I eat it still remains to be the same carbon when it's in the sugar molecule as it is when I breathe it back out as carbon dioxide. And so because of that, that helps us to get a kind of an idea of how the law of conservation of matter works. It's largely because atoms themselves cannot be created or destroyed. So we can't create atoms, we can't destroy atoms, and since everything is made up of atoms, then if we take into consideration the mass of these things, the mass is going to be unchanged no matter what we do with these atoms. And when we say unchanged, we're talking about from before a change to after a change. Even if that change were physical, if something were melting, the weight of that melted object should be the same as the weight before it melted. If we have a chemical reaction, the weight beforehand should be equal to the weight afterwards. So if we think about the law of conservation of matter, it can largely just be broken down into the idea of, whatever's before equals whatever's after. And the part of this we're talking about before is we're talking about the mass before equals the mass after. Or if you want to think about it, the atoms before are going to equal the atoms after. And sometimes this doesn't seem like it might be the case. When we did the lab with vinegar and baking soda, I asked y'all to measure things in a couple different ways because we took the little baggie, and there was one point where we measured the stuff and then we let the gas escape. But if we added the vinegar and the baking soda and we left the bag open, it would look like that there was some weight loss. But there really wasn't any weight loss. The issue was there was a gas made, and when that gas can escape, the gas will escape. And so sometimes it may appear that the law of conservation of mass is broken, but that's only when we have what we call an open system, where something can escape or that something can come in. If we have a closed system like we did when we took the baggie and sealed it up, then there should not be any loss. That total mass should remain the same no matter where it goes, as long as we're still able to weigh it or to determine the mass of that object. So simply, in general, that's really what we're coming to in terms of the law of conservation of mass. That's our statement. And from that, we had a number of tasks that we needed to be able to do. So one of those involved looking at chemical formulas and looking at elements, compounds, and talking about how they would react with one another and being able to account for every atom that would go into something like that. So let's remember, first of all, we discussed subscripts. Subscripts are the little numbers behind an element that tells us how many of an atom we have. So we might have that for H2, we might have that for H2O, so this would be 2 hydrogens and this would be 1 oxygen. So these subscripts help us to be able to count and determine how many of each atom we have. If we had a large molecule like sugar, C6H12O6, we could add all these up. That's 6 carbons, that's 12 hydrogens, that's 6 oxygens. It would be 24 atoms in total. Now the way that this is written doesn't show us anything about how the molecule is put together, but it does show us all the components or all the parts of that particular molecule. The other numbers we've been messing around with are the coefficients, and the coefficients are the big numbers that we end up putting in the front. So if I wanted to say that I had more than one entire molecule, then I could put a 2 in the front. This would tell me I have 2 entire units of sugar. Or if I put a 3 in front of this would tell me that I've got 3 entire units of water. Since each water would be a hydrogen and a hydrogen stuck onto an oxygen, if I put a 3 on the front, it's effectively saying, hey, I'm going to take this and I'm going to multiply it times 3. And if I did that, now I don't have 2 hydrogens, we've got 6 hydrogens, I don't have 1 oxygen, I've got 1 times 3 oxygens. So when we're able to use these subscripts and these coefficients, then it helps us to get an accurate number or an accurate count of how many of each atom are going to go into a particular chemical reaction from beginning to end. And remember the law of conservation of mass, that number at the beginning needs to be the same as at the end. So if I started with 6 hydrogens, I have to end with 6 hydrogens. If I end with 12 oxygens, I needed to start with 12 oxygens. Now, are they able to switch places? Definitely. That's because that's one of the things that atoms are able to do. Again, the carbon that's in this apple, once it's digested, it's not going to stay as a part of this apple. It's going to go through my body. It may end up in a cell. It may eventually become part of carbon dioxide, may come back out of my body. And then it may start all over again. It may end up back in a plant, and the plant will use that carbon dioxide then to build another sugar molecule. So nature and our world continually recycles atoms and recycles elements as we go from building new chemicals from smaller ones or from different ones. So once we have an idea of how to be able to count these atoms that we might have in a particular compound, that kind of leads us into to being able to balance an equation. So for example, we should know that if we take hydrogen gas, again that's diatomic because it's got the little 2 on there, and we take oxygen gas under the right conditions, this can form water. And so if we look at this, we draw this out, hydrogen always sticks to itself. Oxygen will stick to itself. They always come in pairs. But to make a water molecule, I don't get all of these guys over here. Again, we have 2 hydrogens connected to an oxygen. So according to the law of conservation of matter, this doesn't look right. Both of my hydrogens end up, these 1,2 hydrogens end up over here, but my 1,2 oxygens, they don't all end up. And you may say, well, I've just got something left over. We could just have an O over here. But that's not really how it ends up working. I need to account for that oxygen in some way, because what I'm telling you is that hydrogen and oxygen make water. I'm not saying hydrogen and oxygen make water and more oxygen. It's hydrogen and oxygen make water. So in order for us to make a water molecule, we need the right ingredients and then we need the right proportions. It's kind of like cooking in the kitchen. For you to make certain meals and for certain dishes, you need to have the right proportions of things. Sometimes you need twice as much of one thing as you need of something else. Sometimes you need 3 times as much. So in this case, what we need here is, if I start off with 2 oxygens, I need to end up with 2 oxygens. And again, you may look at this and say, well, if I've only got 1 oxygen at the end, why can't I just turn this into just 1 oxygen there? Hey, problem solved, right? Because now I do that and everything's good. Again, the problem is in real life, oxygen doesn't come out this way. In real life, oxygen is always going to be a diatomic molecule. And so it's always going to be a pair. Can't fix that. Well, then you might say, well, why can't we just put a 2 over here? That fixes things. Well, many of you have heard me say H2O is water, but H2O2 is hydrogen peroxide. They're very different chemicals, so we can't just willy-nilly stick another number on the end of it and solve the problem either. So if we want to communicate that we want to take hydrogen and oxygen and make water, then the way we fix that is through the correct proportions. So what I need over here is I need another oxygen. All right, for me to get another oxygen, that means, well, I can't just have an oxygen. I got to have everything else that's attached to it. So I need to have another entire water molecule and the 2 hydrogens that come along with it. So now I don't have 1 molecule, I've got 2 molecules, and I need to indicate that with a 2 in the front. So I've solved my oxygen issue because I had 1, 2 oxygens over here, and now I've got 1, 2 oxygens over here. My problem though is I started off with 2 hydrogens, and now I've got 1, 2, 3, 4 hydrogens. So I need to come back over to this side and say, well, to make this recipe work, I need more stuff to begin with now as well. So not only did I need to have more stuff at the end, now I'm going to have to go back and say I need some more stuff at the beginning. So specifically, I need another pair of hydrogens. So now I've got 1, 2, 3, 4 hydrogens. That's going to balance out 1, 2, 3, 4 hydrogens. And I got to account for both of these boxes I've drawn now and put a 2 in the front. So now we would say that this is a fully balanced equation, because every hydrogen at the beginning, 1, 2, 3, 4, is accounted for at the end, 1, 2, 3, 4, and every oxygen at the beginning, 1, 2, is accounted for at the end, 1, 2. So we can look at this and realize that that's a balanced equation. So in order for us to make hydrogen and oxygen turn into water, that's fine, but specifically I need 2 hydrogens for every oxygen. And that kind of makes sense because in the water molecule, there's 2 hydrogens for every single oxygen. And so to go into the recipe, I need twice as much hydrogen to start with. So again, we can see a lot of different types of equations to try to determine if they're balanced. Some other things you might see, for example, if I had something like magnesium and nitrogen, which is also diatomic, metal and non-metal is going to make an ionic bond, and we would end up with magnesium nitride. Actually, I got that backwards. All right. So we can remember that magnesium is plus 3, nitrogen's, magnesium is plus 2, nitrogen is minus 3. Can't remember if that's what I had to begin with or not. That's how it should be. So in order for me to balance this, this is 3 magnesiums and 2 nitrogens. Over here I've only got 1 magnesium and I've got 2 nitrogens. So I'm a little bit light on the magnesium side, so for me to balance this out, it becomes really simple. I just need to put a 3 in the front. And now I can say that I've got 3 magnesiums, 2 nitrogens, and 2 nitrogens. So if I said this, if I wanted to read this, I've got 3 magnesium atoms plus a nitrogen molecule yields, it's just what we use for that arrow, 1 unit of magnesium nitride. So by putting that 3 in the front, we end up balancing the equation there. The last little piece of this unit was looking at several different types of chemical reactions and classifying them properly, because when we put things together or we break things apart, there's a number of different ways in chemistry that these types of things can happen. So one thing they all have in common is we've got our arrow, because everything's going to start off with an arrow. And on the left-hand side of the arrow, we've got the things that we start with. These are our reactants. And on the right-hand side, we've got our things that are made, which are our products. And there's no real rule about how many reactants or how many products you can have. But when they do show up in certain patterns, we've got some names we classify them. So we may have something where we have 2 objects over here, and it results in 1 product. So effectively, we've got 2 small things going through a chemical reaction and making something that's just going to be a lot larger. So this is what we call a synthesis reaction. If we flip this around and do the opposite, we may have a large compound that breaks apart into 2 or more smaller pieces. And this is called a decomposition. Oops. Ideally, we can just identify those pretty easily, because this one starts with a plus and then is followed with an arrow. This one starts with an arrow and it's followed with a plus. And then we have a couple of different types of reactions that are very similar to one another, and so that there's a plus, an arrow, and a plus. Both of these are called replacements. Sometimes you see it as a displacement. And what we have here, the way that they're different from one another, is we generally have 2 things turning into 2 things. All right. But the way that they end up being a little bit different is that in a single, this is called a single replacement, we have an element and a compound, and that's going to result in an element and a compound. And effectively, if we remember kind of what's going on, if we had A and then we had this compound BX, what happens is the A's and the B's switch places. So we do end up with a different element at the beginning and a different element at the end. We have a different compound at the beginning than we have at the end. But basically, if we are able to identify our pluses and arrows, first of all, if we look at our pluses and arrows, we can eliminate that it's a synthesis or decomposition. So if we see that there's a plus, an arrow, and a plus, then we know it's going to be a replacement. If there's an element on both sides of the equation, then we know it's going to be a single replacement or a single displacement. Contrast that just slightly with the next kind of replacement. Again, the pattern's the same. That starts with a plus, has an arrow, has a plus, but the way that it's different is these are all compounds. So a compound and a compound turn into a compound and a compound. So we still have a replacement, but this is a double replacement. One of the ways we think of it as being double is that one way to keep in mind is all the matter that's involved in this. These are compounds, which are at least two elements put together. And again, the way that it ends up looking is if we had compound AX and it reacted with compound BY, just like in the single replacement, it's really one atom, or excuse me, one element replacing the other. So then what we end up with is A and B switching places. So no longer do we have AX, we have BX, and no longer do we have BY, but we have AY. So these guys are just switching places. So it's a replacement just like we had in the first one, but the difference is that both of these end up being compounds, whereas the other one we have an element on there. So we can identify our synthesis by the order of the plus and the arrow. We can identify the decomposition by the arrow and the plus. We can identify the replacements by plus, arrow, and plus. And then we can differentiate single and double based upon whether there's an element in the equation or whether it's all compounds in the equation. That's the main way that we're going to be able to do that. And then finally, one of the last things just to look at, and then hopefully this is kind of a common sense thing, is that if we actually weighed the materials, that again, if the mass before equals the mass afterwards, and remember we can almost think of this, if I take that away and make it an equal, so the mass before equals the mass after, then that means the mass of all the reactants has to equal the mass of all the products. So if we started off with 100 grams of reactants, we have to end up with 100 grams of products. If we go back to the previous example of all these types of reactions, you know, maybe that 100 grams is broken up into two pieces. So I still, if it was, you know, 60 and 40, just throw some numbers in here. You know, if I had 40 and 60, I would still have to end up with 100 over here. And again, this could also be, I mean, it could be 30 and 70. It could be any combination. But these two numbers added together are going to have to add up to the number that we have over here. If we did a decomposition, same thing. If I started off with, say, 200 grams, then whatever I end up with at the end, these two things are going to need to add up to 100 grams. So maybe it's 150 and 50. Same thing with our replacements. If I had, scroll down so it's not quite as messy. You know, if I had 100 grams of something plus 50 grams of something, and it was a replacement reaction, you know, if I knew that one of my products was 75 grams, then I should be able to figure out what number goes here as well, because if I add those together, it needs to equal what both of these would be together. So 150 would need to equal 150. So then I just need to say 75 plus what, or 150 minus 75 gives me this other piece over there. And do they have to be equal? No, they don't need to be equal, and they're probably not going to be equal. It could be any combination. But again, the math has to work out that the mass of whatever we start out with has to end up equaling the mass of whatever we end up with. No matter what type of reaction we have, any of those four reaction types that we have, the mass before the reaction has to equal the mass after the reaction. The total mass of the reactants has to equal the total mass of the products.